Hi dear students, welcome to the next question from the question discussion sessions of moving charges and magnetism. So let's continue with the question number 14. Okay. Question number 14. A square current carrying loop is suspended in a uniform magnetic field. Remember one thing, a square current carrying loop is suspended in a uniform magnetic field. So in a uniform magnetic field, total force equal to 0 and torque is not equal to 0. If the force on one arm of the loop is capital F, then the net force on the remaining arm of the loop, total force will be equal to 0. We need to get the total force. So in a uniform magnetic field, so let's consider this a uniform magnetic field, a current carrying loop is placed. For one arm it is F. We know total force will be equal to 0. So this is the one side, this is given as F1, this is second side F2 and this is third side F3. So total force equal to 0 means F1 plus F2 plus F3 plus capital F equal to 0. Total force will be equal to 0. Magnitude of total force. Magnitude of total force will be equal to 0. So F1 plus F2 plus F3 question is asking. So F1 plus F2 plus F3 is equal to minus F. Minus F. So total force on the remaining three arms is equal to minus F. Then only minus F plus F will be equal to 0. Total force equal to 0 when a current carrying coil is placed in a uniform magnetic field. So answer to the 14th question is option B. Let's move to the 15th question. 15th. What is the 15th question is speaking? A straight section of PQ of a circuit lies along the x-axis from x is equal to minus a by 2 to x is equal to a by 2 and carrying a current I. So we have an x and y axis. So here we have one wire which is located at x is equal to minus a by 2 to x is equal to a by 2 area. It is located. And this is carrying a current of I ampere. That is also given in the question. Magnetic field due to the sections PQ. So the section is called PQ. At a point x is equal to plus a. So I need to find out what is the magnetic field at x is equal to a. We have learned if it is a current carrying conductor then the magnetic field along the axis of the current carrying conductor is equal to 0. Magnetic field at a perpendicular distance d from here. So here magnetic field B is equal to mu 0 I divided by 2 pi d. This is also we have learned. Which of the following condition is matching will be here. Here it is along the axis. So this condition, it's along the axis. If it is along the axis, magnetic field along the axis B is equal to 0. Magnetic field is equal to 0. The same thing we have seen in our second question. Okay. Hope you remember our second question. In our second question we have find the magnetic field at here. So due to the conductor number 1, this is along the line. So B1 equal to 0. There we have given this as 1, this as 2 and this as 3. So for 3 also this point is along the conductor. So magnetic field is equal to 0. So along the axis it is equal to 0. This information we have already seen it in question number 2. Question number 2 we have already seen this informations. Okay. Perfect. Fine. Okay. So let me clean the board and we'll move to the next question. So 15th answer is what? Answer alone I have not marked. What is the 15th answer? Answer is 0. So 15th answer is option D is the right answer. 0 is the correct answer for the question. Okay. So let me clean this one and we'll move to the next question. Question number 16. You can read it, the question number 16. What is given there? In question number 16, it is given A and B of two conductors carrying the current I in the same direction X and Y are the two electron beams moving, only two electron beams moving in the same direction, then if two conductors are carrying current in the same direction, so two conductors carrying current I1 and I2 or I and I2 carrying in the same conduction, then what type of force is existed? Attractive force exists. Attractive force exists. If two conductors are carrying current I1 and I2 in opposite direction, then what type of force will be there? There will be a repulsive force acting on the body. So attractive force will be there and repulsive force will be here. This is in case of a conductor. Now there is a two electron beams. Okay, this is an electronic charge, this is a charge. So here Coulomb force will exist, 1 by 4 pi epsilon 0 q1 q2 divided by r square. Coulomb force will exist, equal charges. So what type of force will be here? A repulsive force. This is only for two electron. Two electron means it's just a charge. So charge between them, it's a repulsive force. So what is matches with this option? Option B, there will be an attractions between A and B because they are carrying current in the same direction, and there will be a repulsions between X and Y. X and Y are the two electron beams. So answer is to the question is option B. Let's move to the 17th question. 17th. A galvanometer of resistance G is shunted by a resistance of S ohms. To keep the main current in the circuits unchanged, resistance to be put in series with the galvanometer. A galvanometer whose resistance G is shunted with a resistance of S ohms. The key point will be here, to keep the main current in the circuit unchanged. So remember this point, to keep the main current in the circuit to be unchanged. Which means that what? Initially I have only galvanometer which is passing a current of I and output is also given as I. And now what we have done means we have a galvanometer and it is connected with a shunt resistance of S, and the whole combination is now connected with another series resistance called S dash. So if you do like this one, I want to get the total current still should be unchanged. After doing all these arrangements, I want the current should be still to be unchanged. So here current is equal to voltage by resistance, of course we know. So here only galvanometer. So if the total resistance of this system is equal to this resistance, then the current is unchanged. Okay, so which means that what? So here currents are same. If currents are same means what should be there? Resistance must same. Resistance must be same. Resistance must be same. So if both resistance are equal means I can 100% say currents are same. So the resistance here, this total resistance should be equal to what resistance? Galvanometer resistance. What is this resistance value? Parallel combination GS divided by G plus S and plus S dash. S dash value we need to find out. What would be the resistance I have to put in series to the galvanometer so that the entire system is having the same current of previous situations. We need to solve this out. Okay, so let me go and solve the steps. You can solve, you don't want to wait it for me till I am solving. So S dash will be equal to G minus GS divided by G plus S. So we'll solve this G square minus GS, G square minus GS whole divided by G plus S. G plus S. So how we can solve this one? The final steps of this one. How it is coming? So it is G square minus 2GS whole divided by G plus S. So if I am taking G as outside, or minus G if I am taking outside, or G if I am taking outside, what will come? G minus 2S will come divided by G plus S. S dash will be equal to G minus GS G square G square plus GS, like this, G square plus GS minus GS. So here it will cancel, here only G square will come. Okay, here only G square will come, because this and this will get cancelled outside. So answer is G square divided by G plus S. 17 G square divided by S plus G, which is equal to G plus S. So 17th option is C. Answer is C to this question. Okay. So let's move to the next one, 18th. So the current to keep the same, resistance of the previous condition will be equal to resistance of the current conditions. Remember the points. Okay. Fine. Perfect. 18th question, there is a big derivations are there, but you don't want to do the derivation or remind the derivations. Only at the moment you have to remember the formula. A current I flows in an infinitely long wire with the cross section in the form of a semicircular ring of radius r. Magnitude of magnetic field induction along the axis. You can remember, okay, you can imagine like you have a current carrying conductor, a pipe in the center we are cutting this pipe in the center we are cutting. Once we are cutting to the center of the pipe, so what you will get a half circle, correct? You will get a track. Okay, remember you have a pipe and their center, exactly center you are cutting, so you will get a half circle kind of structure. That half circle kind of structures, I keep it and bend in this format. Then the magnetic field at the center will be equal to, for this half circle will be equal to mu 0 I divided by pi square r. This value you can remember. There is a complex derivations will be there, but that is not required for you. It's not there in your syllabus. In case if it is asked for like AIMS kind of examination previously, so there is a big chance to ask this also. B is equal to mu 0 I by pi square r. Just remember this and take a note of this one. That's all. Answer is D, option D. So 19th questions will move. 19th one. Two electric current flowing perpendicular to each other as shown in the figure. AB, CD are perpendicular to each other and symmetrically placed with respect to the current flow. Where do we expect the resultant magnetic fields to be 0? Where resultant magnetic field is 0? Two current carrying conductor is placed. One is A, O, B. This is one conductor. And another path is like C, O, D. This is a two lines there, not a conductor. So two currents are carrying. One is here I and one is here I. Where the magnetic field will be equal to 0? That was a question. Where and all magnetic field will be equal to 0? So we know these are having equal current. So to find out the magnetic field, we know the formula for a conductor B is equal to mu 0 I by 2 pi r. But they are not expecting as a formula. Just a logic. At which line? Where AO magnetic field 0 or OB 0 or CO 0 or OD 0, this is what they are asking. So how to find out the direction of magnetic field from the current? We will use right hand thumb rule. So thumb is pointing the direction of current. If you place it like this, you can see bottom side. So other curling fingers are representing the direction of magnetic field. Correct. So this is my thumb. Thumb is pointing in the direction of current. So I am curling my fingers like this. So bottom side it is into the board and here it is out of the board. So here it is into the board. Two circle I am asking. Here it is out of the board. So that is clear with respect to this. Next we'll go to this conductor. This conductor will give rise to, the thumb is pointing upside and other curling fingers are coming. So right side it is into the board. So right side it is into the board and left side it is out of the board. Because of this conductor here into the board and here it is out of the board. So hope I have marked. So because of this conductor the x-axis conductor, bottom it is inside and top it is outside. Outside means dot, cross means inside. See, you can see if I am placing my fingers like this, my thumb is going inside here and it is rotating and it is coming outside my other curling fingers. So the magnetic fields are like this for this conductor. For this y-axis conductor, right side my fingers are going into the board. That's what these two cross marked, and left side it is coming out. Okay. So 4 lines I am marking for the y-axis conductor. Now if you see will be here in the sections A, this is magnetic fields are into the board, magnetic fields are out of the board. Cross with the dot will cancel. So here I can say magnetic field is equal to 0. Here because of this magnetic fields are inside the board, because of the y conductor magnetic fields are inside the board. So magnetic field at inside will be there, which is not equal to 0. If you see here both are outside, so magnetic fields at outside is not equal to 0 because of this and because of this. Magnetic fields are vector quantities, both are pointing in the same direction, so it will get added up, it will never cancel. But if you see will be here, magnetic fields are inside the board, magnetic fields are outside the board. Inside minus outside, both are in opposite direction, same magnitude. Why same magnitude? Because same current will be there at a particular distance. At a particular distance means because of the current carrying conductor, magnetic field is mu 0 I by 2 pi dt. It depends upon current, it depends upon distance. At a certain distance, equal distance from x and y axis, and current will be also will be the same. So here magnetic field directions are inside and outside. So here B in and B out. Here this is also B in and B out, both are cancelled, so magnetic field equal to 0. So where the magnetic fields are 0? Magnetic fields are 0 on the first quadrant and third quadrant, which means AOB line magnetic field is equal to 0. So that is matches with which options? On AB line. On AB line, AB line means AOP or AB line specifically. So 19th option A is the right answer. Option A is the right answer for 19th question. Hope this is clear. Nothing we have done. We are used our right hand thumb rule to find out the direction of magnetic field. Thumb is representing the direction of current. Other curling fingers are representing the direction of magnetic field. So that's what we are applied. And when we see magnetic fields are acting in opposite direction, it will cancel each other. So that is the stuff behind this portion. Okay, we'll move to the next question, question number 20th. Next question, question number 20th. What is question number 20 specifying? A closed loop PQRS carrying a current placed in a uniform magnetic field. Uniform magnetic field, previously I told total force will be equal to 0. Total torque is not equal to 0. If the magnetic force on the segment PS, SR and RQ are F1, F2, F3 are respectively given and perpendicular to the plane of paper along the direction shown here. Force on the segment QP. So listen. So this is what is the structures we have. So at the center there are forces are acting here F1 and here F3. This is not the same line. That is the slant positions will be here because different length F2. So we need to find out PQRS. So PQRS. We need to find out what is the force on the segment QP. Means this one. We have to find out. So to do this one, we have to do certain applications. See, there is a difference. This is this much segment length. This is this much segment length. And there is a difference in force will be there. What is the difference in force? Up to here F1. This F1 with F1 cancel. Balance is what? F3 minus F1 will be there this side. And this side is same as this one, which is given as what? F2, right? This is F2. And if two sides of the triangles are given with a force of F3 and F1, how we will find the third side? Third side will be equal to the resultant of third side, root of A square plus B square plus that formula, right? Okay, so resultant of two forces we have to find out. So how we will find out the resultant of two forces? R equal to root of a square plus b square, resultant of two vectors, if minus 2ab cos theta. Okay, so ab cos theta, theta is the angle between them. If a is in this direction and b is in this direction, if two vectors are in the same direction, then what we'll do, okay, sorry for this one, r equal to root of a square plus b square plus 2ab cos theta. If there are two vectors which are acting in the same direction, if two vectors a vector and b vector acting in the same direction, so here theta equal to 0 degree. So in this case, resultant will be equal to root of a square plus b square plus 2ab cos theta is 0. So which is equal to root of a plus b the whole square, which is equal to a plus b. Two vectors, same directions, we are adding up. Okay. So here theta, I am saying to say theta is the angle between two vectors. Here two vectors are this one. This is one. F3 minus F2, and this is another side. So these two sides angles are 90 degree. So the cos 90 is 0. So the resultant of two vector is F2 square plus F3 minus F1 the whole square. So resultant, these two will give a resultant of this one. So this resultant should maintain here, so that what will happen, the total force will be equal to 0. If ഇതിന്റെ value 2 ആണ്. Okay, ഇതിന്റെ value 2 ആണ്, ഇതിന്റെ value 3 ആണ്. So if these two values are 2 and 3, for example, you assume, so root of 2 square plus 3 square, 4 plus 9 root 13. Root 13 has to come, will be here, because these two will give a resultant force, and that resultant force should cancel with the force given by PQ. Then only total force equal to 0. In the previous question we have seen, in a pure square loop, one side it is f. So all the three sides together, what should come? Minus f in a straight format. But here it is not a perfect shape like a square. It is not like a square. It's I can say it's a combination of a square or a rectangle plus a triangle. So here it is f1, means this is also equal to f1. So this f1 will get cancelled, but this f2 will come here, and the balance, the difference, f3 minus f1 will. So these two will give a resultant force. That resultant force must apply by this PQ side to cancel the resultant of these two forces. Okay, so these two will give a resultant force. You can assume that resultant force will be equal to 100 Newton. So that will be acting in one direction. So definitely another 100 Newton should be there to act in opposite direction to cancel the resultant of these two. So what should be the other force which is acting? That is also equal to 100. So that's what it's doing here. Okay, hope this is clear to you. Total force always equal to 0. Fine, let's move to 21st question. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter is halved, then the new value of magnetic field. So 21st question, the magnetic field due to a solenoid equal to mu 0 Ni, where N will be equal to number of turns per unit length. Okay, now the new B dash will be equal to, current is doubled and the number of turns is halved. N become N by 2. N become N by 2 means small n also become, here N become N by 2, which means small n will become N by 2. So which is given, number of turns per centimeter is halved. This is number of turns per length. Okay, N become N by 2 into current become 2I. So again 2 will get cancelled. B dash will be equal to mu 0 times of Ni, which is equal to P. So it's a very straightforward question. 21 answer is C. Number of turn, this do not confuse with the small letter n, capital letter N. Small letter n is number of turns per centimeter or per meter. Per meter, if you see that question, then that is called small letter n. If they are saying simply number of turns 100, number of turns 100, number of turns 50, then that is called capital N. So remember, I already told while I am taking theory, this is simply called number of turns, that's all, it's a number. This is called a number of turns per meter. In SI system, it is per meter, in CGS it is centimeter. So whatever the question is given to you, you have to convert into meter. So number of turns per meter. Okay. So fine. 21st is fine. We'll move to 22nd question. 22nd. A particle of charge q and mass m moves in a circular orbit of radius r with an angular speed omega. Ratio of the magnitude of magnetic moment. Ratio of the magnitude of magnetic moment to the angular momentum. M by L. I told q divided by 2m. We have taken this in the theory. Magnitude of magnetic moment to the angular momentum is equal to q by 2m. This is a formula. And it is depends on what? It depends upon q and m. It's a very straightforward question from the class note. 22 answer is option C. We'll move to the next question. Question number 23. A current loop in a magnetic field can be in equilibrium one direction? No. Can be equilibrium in two orientations, both equilibrium states are unstable equilibrium. Can be equilibrium in two orientation, one stable while other unstable. This is very deeply I have taken in the theory sessions. When a current carrying coil is placed in a magnetic field, there if you go to that section in the class notebook and read it there we have specified about stable equilibrium and unstable equilibrium. So there are two equilibrium positions will be here. Torque is equal to m cross b. Torque is equal to m cross b, which is equal to mp sin theta. When theta equal to 0, torque is equal to 0. This condition is called what? This condition is called stable equilibrium. This condition is called stable equilibrium. Another one, theta is equal to 180 degree, torque is equal to 0. This is called unstable equilibrium. Very detailed explanations I have given in the class notebook. Please read that. But here question is a straightforward question. So we can one stretch answer from the class notebook itself. 23 answer is C. It's there in the class notebook while I am taking the theory part. It is very detailed. I have explained that. Theta equal to 0 is called stable equilibrium. Theta equal to 180 is called unstable equilibrium. The reason is also have specified there. Okay, so please read that if you have not remembering at the moment. Just pause the video, take 5 to 15 minutes of time and read that thoroughly, then come to here so that you will easily remember this part. Okay, so we'll move to the next question. Question number 24. What is question number 24 specifying? Two long parallel wires P and Q are held perpendicular to the plane of the paper with a distance of 5 meters between them. If P and Q carrying a current of 2.5 ampere, 5 ampere respectively in the same direction, then the magnitude of magnetic field at a point half pi between them. So this is a current carrying conductor. What is carrying 2.5 ampere? One is carrying 5 ampere. Magnetic field will be here. You can see at the center, what is the distance between them? Distance between them, it is given as 5 meter. So from center it is 2.5 meter. Here also it is 2.5 meter. The question is like what they are asking for us. What is the magnitude of magnetic field at the center point? Here we have to find it out. So because of this thumb, because of the thumb, it's pointing in the direction of current, and the magnetic fields are because of 5 ampere it is outside. So I am writing B5 out. So because of 2.5 ampere magnetic fields are inside. So B 2.5 in, I am writing. So two magnetic fields are in opposite direction. We have to find out the total magnetic field B net equal to higher value minus lower value. Higher value means 5 ampere current is the higher value. So B5 out minus B 2.5 in. What is the magnetic field due to a current carrying conductor? The formula is mu 0 I1 divided by 2 pi d minus opposite direction. Vector opposite means mu 0 I2 divided by 2 pi d. So mu 0 divided by 2 pi, distance to the center point 2.5 meter. I am writing as 5 by 2. 5 by 2 is 2.5 into I1 minus I2. I1 is 5, I2 means 2.5. So we'll simplify this part. So here 2 will get cancelled. So mu 0 divided by 5 pi into 5 minus 2.5. 2.5 again writing as 5 by 2. 5 cancel. Answer is mu 0 by 2 pi. Answer is mu 0 by 2 pi. Option C is the right answer for 23 answer is, sorry, for 20, okay, this is for 23. 24 answer is C. Mu 0 I divided by 2 pi. Mu 0 I divided by 2 pi, option C. 23 also C. So 23 C, 24 C. Okay, hope this is clear. Two current carrying conductor, one magnetic fields are outside, one magnetic fields are inside. So outside minus inside. Why we had done outside minus inside? Because outside current will be higher, distance are same. So the net magnetic field direction is what direction? Outside is higher. Higher minus a lower value we are subtracted and we get a higher value, a positive number. So the net magnetic fields are also in the direction of outside. Outside will be the higher values. Correct? Okay. Normally we will say 5 minus 2 will written as 3. So 3 means this is plus, this is minus. So the answer having the sign of the highest number. So what is the number? 3. So B out is positive. B 2.5 is negative, right? Negative. This is positive. So positive, negative. So what you will get? Positive. Positive means what direction? B5 out in the direction. So B5 out is outside. So it's outside. Sorry, outside magnetic field. Mu 0 I by 2 pi. Okay, hope this is clear. We'll move to the next question, 25th. If you learn the class notebooks, so that it's very easy to do the questions and practicing it more and more. 25th. Okay, what is given the question? A very long straight wire carries a current I. At the instance when a charge plus Q at a point P has a velocity as shown in the figure. Force on the charge carrying conductor. So here we have a current is moving. Here an electron is moving in the direction of V. Okay, a charge Q. See, if a current is moving in this direction, the right side, the magnetic fields are inside. Here it is outside. So magnetic fields are into the board, magnetic fields are out of the board. So force direction they are asking. So to find out the force direction, what will use? Fleming's left hand will use. In Fleming's left hand rule, your thumb is giving the direction of magnetic field, middle finger will be giving the direction of velocity. So we'll place it like this one. So it's in the direction of velocity, this finger, and my thumb, it is into the board. So my force is in force, thumb is giving the direction of force. Force is in what direction? It is in upside direction. So this directions my force will be there. So Fleming's left hand rule. So application of Fleming's left hand rule. That's what we have done. We have applied the Fleming's left hand rule. Here velocity is in what direction? Plus x direction. Velocity is plus directions. Okay, and the magnetic fields are into the board. Into the board means minus k direction, or I can say minus z direction. Minus direction. Okay, so by applying the Fleming's left hand rule, we got force in the positive y direction. or you can do like this one. We also know V is equal to Q into V cross B. Direction is only important. So Q into direction of V is I direction. So I cross minus K. So we know this circle, right? I, J, K. I cross K is minus J. I cross, here minus will be there. This minus is taken outside. So minus Q into I cross K. I cross K, opposite. I cross K is what? Minus J. So minus Q into minus J. What you will get? Plus Q J direction. So Q is just a charge. So Q J. J means what direction? Positive Y direction. Positive Y directions. You can use mathematical formula or you can use the Fleming's left hand rule. Both ways it is correct. This is along the OY direction. Answer is 25. Answer is option A. 25 answer is option A. Okay. Fine. We'll move to the next question. Question number 26. Fine, perfect. Yes, question number 26 will move. Question number 26. Two wires carrying 2 ampere, 1 ampere are enclosed in a circular loop. Another wire with a current of 3 ampere is situated outside the loop as shown in the figure. The closed integral B dot dl. So closed integral B dot dl's Ampere's law mu 0 times of current enclosed. So B dot dl they are asking, so mu 0 times of current enclosed within the circle. So two currents which are in the opposite direction. So the resultant current is 2 minus 1. 2 minus 1 is 1. Answer is mu 0. Answer is simply mu 0. 26a. This is I have not seen these questions are frequently asked, but there is a I see a chance to ask this kind of question in the coming NEET examination. I hope so. Fine. So we'll move to the next question. Question number 27. We have space will be there. So we'll move to question number 27. If in a circular coil A of radius R and carrying a current, and in the another coil B of radius 2R carrying the current 2I, then the ratio of the magnetic field B and BB produced by them. So if in a circular current carrying coil, the magnetic field at the center mu 0 I by 2R. So here we have two cases. The first one for the conductor number A. Question is asking the magnetic field produced by them will be at the center. Okay, at the center word is missing in the question actually. So you can add it to the question at the center. Okay, they have not specified the point where we want to be find out. So by default we are studying at the center and we are studying at the axis. So I am assuming here at the center. Question is not giving at the center. So you can add produced by them will be at the center at the end of the question. So BA will be equal to mu 0 I divided by how much will be coming? Radius R 2R, and BB second magnetic field will equal to current will become doubled and radius will become also doubled. Both will get cancelled. So this is equal to mu 0 I divided by 2R. This is nothing but equal to BA. So what the question produced? The ratio of the magnetic fields produced BA to BB is what? Both are equal. So answer is 1. Answer is 1. So 27th option A is the right answer. Option A is 1. Option A answer is 1. Okay. We'll move to the next question. Question number 28. Question number 28. A charged particle moves through a magnetic field perpendicular to its direction. When a charged particle is entering a perpendicular magnetic field, it will undergo circular motions with constant speed. If I say constant speed, I can say constant velocity in terms of magnitude, but in terms of direction, velocity is not constant. Okay, in a circular motion, what is different? Speed constant here. In this case, speed constant, velocity not constant because direction changes. because direction changes. Now we'll look into the question. What is given? Kinetic energy changes, momentum changes, kinetic energy changes. We'll see momentum. Momentum vector P is equal to m into vector v. Velocity v is changing. V is changing means magnitude is not changing, direction is changing. So definitely P changes. Definitely P changes. Next one, we'll look into kinetic energy. What is kinetic energy? Will be equal to energy is a scalar quantity or vector quantity. Energy is a scalar quantity. So I need only the magnitude of V. Here only magnitude of V, because kinetic energy is a scalar quantity, don't bother about directions. So magnitude of V is constant, so kinetic energy is constant. Now can you tell me the answer to the 28? Momentum changes but the kinetic energy is constant. 28 answer is option B. So when a charged particle enter into a magnetic field, it will undergo circular motions with constant speed. Velocity, direction is keep on changing. Because of the changes, momentum changes but the kinetic energy remains constant. Okay, hope this is clear to you, and I'm stopping here and we'll continue in the next sessions with the from 29th onwards. Okay, so thanks for listening the video. Hope today's question discussion is understood to you. So learn the theory notebook in case if you are not remembering certain formulas, certain equations and certain concepts. Okay, thanks.